Every moment, space itself grows larger. Not by inches, not by miles, by thousands upon thousands of miles every single second. The gulf between distant galaxies widens at speeds that defy comprehension. And here's the part that shatters everything you think you understand. This expansion doesn't happen into anything at all. No outer edge exists. No container waits to be filled. No vast emptiness surrounds our cosmos, ready to receive its growth. We're about to explore the single, most reality-breaking idea in all of physics, how the universe creates space from absolute nothingness, the invisible phenomenon ripping existence apart at the seams, and why the question itself, what does the universe expand into, makes about as much sense as asking what happened before time began. If this journey expands your mind, hit that subscribe button for Late Space. Let's begin this exploration into the impossible. Take any balloon and blow air into it. Watch how the rubber surface pushes outward. The material stretches because space exists for it to occupy. Your room provides that external volume. The balloon moves into the air around it, displacing molecules, claiming territory that was previously empty. This process makes complete intuitive sense. Every expansion we witness in daily life follows this pattern. The balloon needs somewhere to go. This represents how our brains comprehend growth and change. Cosmologists describe an expanding universe, and your mind immediately constructs that balloon image. You visualize space pushing outward into something. Some enormous container must exist. Some boundary must separate our cosmos from whatever lies beyond. Your intuition demands this framework. It feels not just natural, but mandatory. This is precisely where physics demolishes your assumptions. The universe bears zero resemblance to that balloon. During cosmic expansion, space doesn't push into anything whatsoever. No cosmic container exists. No exterior region waits outside. No boundary divides inside from outside. Space generates the very framework of existence as it grows. Consider this thought experiment. Imagine sketching a circle larger than your paper allows. Rather than finding bigger paper, the paper itself expands to contain your drawing. This seems logically impossible in our experience because everything we know expands into something else. Trees grow into air, urban areas spread into wilderness. Frost extends across water surfaces. Always, expansion requires somewhere to expand toward. Always, a clear boundary exists between the expanding thing and its destination. But what happens when you are simultaneously the paper and the ink? Scientists uncovered this reality-warping truth by observing galaxies in motion. Edwin Hubble detected that more distant galaxies recede from us at greater velocities than nearby ones. Initially, this pattern suggested we occupy the explosion center, as if we're positioned at ground zero while everything else flies outward into empty space. The actual explanation proved far more bizarre. Space itself undergoes stretching. Galaxies aren't traveling through space like ships through an ocean. The space separating them expands. Picture dots marked on a balloon surface as someone inflates it. The dots grow farther apart without moving across the rubber. The rubber itself expands beneath them. Each dot observes all other dots moving away. None occupies a special position. None sits at the center. Now replace that two-dimensional balloon surface with the three dimensions you inhabit. The universe doesn't expand into anything because no anything exists for it to expand into. It manufactures the very stage on which expansion can occur. This revelation shattered human intuition so completely that even Einstein initially resisted it. Yet this seemingly impossible expansion proceeds right now, faster than your mind can process. How can we verify this bizarre process actually occurs? The evidence appears in how light itself gets tortured during its journey through expanding space. When distant galaxies emit light beams toward Earth, that light starts with specific wavelengths: blue, red, infrared, each wavelength carrying a unique signature like a fingerprint from the cosmos. During the light's voyage through expanding space, something remarkable happens. The space through which light travels grows larger while the light moves through it. Imagine walking across a moving walkway that continuously stretches as you progress. Your steps maintain constant size, but the surface beneath you keeps elongating. When you reach the end, you've travelled much farther than your steps alone should have carried you. Light experiences something analogous, except instead of travelling farther, its wavelength extends. Blue light from a distant galaxy arrives at our instruments as red light. This doesn't happen because the galaxy moved away like an ambulance, changing its siren pitch through the Doppler effect. The light becomes redder because space itself expanded during the light's billion-year journey through the cosmos. Each light wave gets pulled longer as the cosmic fabric stretches beneath it. This phenomenon, cosmological redshift, proves that space grows independently of the objects it contains. Consider this staggering number. Light from the most remote observable galaxies is stretched to nearly 40 times its original wavelength. The space that light traversed expanded so dramatically that what began as intense ultraviolet radiation reaches us as faint infrared warmth. Wavelengths 40 times longer mean the universe expanded by a factor of 40 during that light's voyage. Here's what makes this even more mind-bending. This stretching doesn't occur somewhere distant. It happens everywhere simultaneously. Right now, the space in your room attempts to expand. The space between your eyes and screen wants to grow. You don't notice this expansion because electromagnetic forces binding atoms together far exceed the expansion rate. Only across enormous cosmic distances does this expansion become detectable. The space between galaxies lacks atomic forces to hold it together. Therefore it expands freely, transporting those galaxies along like fruit suspended in rising bread dough. The fruit doesn't move through the dough rises and carries them apart. This is why the question, what is the universe expanding into, collapses so utterly. You're asking what the dough expands into, but you exist within the dough. We inhabit the ultimate cosmic prison, and its walls consist of time itself. Step outside on any clear night and gaze upward at stars. You feel as though you're witnessing the universe, the complete thing, all of reality stretched across that dark expanse above. But here's the truth that will reshape your conception of existence. You're observing less than 4% of what actually exists out there. You're confined inside an invisible sphere. This sphere possesses a radius of approximately 46 billion light-years. Beyond this limit lies more universe, billions more galaxies, trillions more stars, potentially other versions of you absorbing these words, but you will never observe any of it. Not with any telescope humanity could ever construct. Not with any technology that could ever exist. The trap isn't constructed from barriers or walls. It's built from the finite speed of light combined with the finite age of our cosmos. Light requires time to travel. When you observe our sun, you see it as it appeared 8 minutes ago. When you look at Proxima Centauri, our nearest stellar neighbour, you observe it as it was 4 years ago. Observe the Andromeda Galaxy, and you peer 2.5 million years into history. The farther you look into space, the deeper you peer into the past. Here's where the trap seals around you. The universe has existed for 13.8 billion years. This means the oldest light that could possibly reach you has been travelling for 13.8 billion years. Any galaxy farther than this might as well not exist from your perspective. Its light simply hasn't had sufficient time to reach you yet. But the trap becomes even more confining. Remember that space has been expanding this entire duration. That distant galaxy resided much closer to us when it emitted the light we detect today. By the time its ancient light reaches our instruments, expansion has transported that galaxy far beyond the 13.8 billion light-year mark. Today, that galaxy sits roughly 46 billion light-years away from us. This creates your cosmic prison cell. Everything beyond 46 billion light-years from Earth exists in what scientists term the unobservable universe. You cannot see it. You cannot detect it. You cannot prove it exists. Yet logic and mathematics insist it must be there. The most ancient light in existence screams toward you right now at 600 million miles per hour. It carries a message from the moment reality began. This light has been travelling longer than Earth has existed, longer than our solar system formed, longer than our galaxy assumed its current shape. This light began its journey when the universe was merely 380,000 years old, back when the cosmos was a seething plasma so hot that atoms couldn't even form. We call this ancient radiation the cosmic microwave background, and it permeates everything. Tune an old television between channels and roughly 1% of that static derives from this primordial light. You're literally observing the afterglow of creation flickering across your screen. This radiation fills every cubic inch of space. It arrives from every direction simultaneously. It's the oldest phenomenon human eyes can detect. But here's what makes this discovery so profound. This light represents the edge of everything we can observe. Before that moment, 380,000 years after the Big Bang, the universe was opaque. Imagine attempting to see through the sun's surface. The early universe resembled that everywhere, a dense fog of plasma that blocked all light. No photon could travel more than a few inches before colliding with charged particles and being absorbed. Then something miraculous occurred. The expanding universe cooled sufficiently for protons and electrons to combine into the first hydrogen atoms. Suddenly the cosmic fog lifted. The universe became transparent. Light could finally travel freely across space. The first photons that escaped this cosmic clearing are the ones reaching your eyes today as the microwave background. This moment, called recombination, created the ultimate horizon. You cannot see past it ever. Any events that occurred during those first 380,000 years remain forever hidden behind an impenetrable wall. The cosmic microwave background is that wall, and it represents the absolute limit of observation. This horizon moves every second that passes. Light that has been travelling for 13.8 billion years plus 1 second reaches us. The observable universe grows by 1 light second every second, about 186,000 miles of new space coming into view. Every day we can see about 16 billion miles farther into the cosmos. Past the edge of everything you can see lies more of exactly what you can see. This sounds mundane, but it's actually the most unsettling possibility in cosmology. If you could somehow teleport 47 billion light-years away, beyond your observable boundary, you'd find yourself in a region that looks remarkably similar to here. More galaxies, more stars, more planets, possibly more life. The universe appears homogeneous on the larger scales. Homogeneous means uniform, the same everywhere, like perfectly mixed batter where every spoonful contains identical ingredients in identical proportions. Our observations of the cosmic microwave background suggest the universe possesses this property. This smoothness reveals something profound about what lies beyond our sight. If the observable universe contains roughly 2 trillion galaxies, then an identically sized region just beyond our horizon should contain roughly 2 trillion galaxies as well. But here's where this becomes psychologically disturbing. If space is truly infinite and homogeneous, then every possible arrangement of matter within any given volume must repeat somewhere. This isn't mystical thinking, it's mathematical necessity. With infinite space and finite ways to arrange a finite number of particles, repetition becomes inevitable. This means there are other versions of you reading these words right now, not metaphorically, literally. An infinite universe that expands presents one of the most beautiful paradoxes in physics. How do you make infinity bigger? Mathematics tells us this should be impossible. Infinity plus anything equals infinity. Infinity times 2 equals infinity. You cannot add to something that already encompasses everything. Yet our observations clearly demonstrate that space is expanding everywhere. The resolution comes from understanding what expansion actually means. When we say the universe expands, we don't mean it grows larger in the sense of becoming more infinite. We mean the scale of space itself increases. Imagine an infinite sheet of graph paper where each square measures 1 inch wide. Now imagine stretching that paper so each square becomes 2 inches wide. The paper remains infinite. It still contains infinitely many squares, but the distance between any 2 marked points has doubled. This is exactly what occurs during cosmic expansion. The universe doesn't become more infinite. The scale factor of space increases, making all distances grow proportionally. But this creates a disturbing implication. If the universe is infinite now, it was also infinite at the moment of the Big Bang. This means the Big Bang wasn't an explosion of matter and energy from a single point into empty space. It was the simultaneous expansion of infinite space filled with infinite energy at every location. The Big Bang happened everywhere at once across infinite space. There was no center, no edge, no outside, just infinite space suddenly beginning to expand and cool. The universe manufactures new space from pure nothingness at a rate that would make every factory on Earth weep with envy. Every second, the volume of observable space increases by roughly 10 to the power of 78 cubic meters. All this new space emerges from the quantum vacuum. The quantum vacuum isn't the empty void you might imagine. It's a seething foam of virtual particles popping into existence and annihilating each other in timeframes shorter than the smallest measurable instant. This process, quantum fluctuation, fills every point in space with energy. Even in the most perfect vacuum, this quantum activity continues relentlessly. Here's the mind-bending part. This vacuum energy has gravitational effects. But unlike matter, which pulls things together, vacuum energy creates repulsive gravity. It pushes space apart. The more space you have, the more vacuum energy you get. The more vacuum energy you get, the more space expands. The more space expands, the more room exists for new vacuum energy. This creates a runaway process. During the universe's first tiny fraction of a second, this process ran wild. Space expanded faster than light could travel, not because anything moved faster than light, but because space itself grew faster than light could cross it. In less than a trillionth of a trillionth of a trillionth of a second, a region smaller than a proton expanded to roughly the size of a basketball. This sounds like science fiction, but quantum mechanics demands it. The uncertainty principle tells us that energy can be borrowed from the vacuum as long as it's repaid quickly enough. During inflation, the universe borrowed massive amounts of energy to create new space, then used the expansion itself to repay the debt. The process worked brilliantly. It overshot, creating far more space than necessary. Our entire observable universe represents just one tiny patch of the vastly larger inflated region. When scientists calculate how much energy the vacuum should have based on quantum field theory, they get an answer that's 10 to the power of 120 times larger than what we observe. This represents the worst prediction in the history of physics. Either our understanding of quantum mechanics is fundamentally flawed, or some unknown mechanism cancels out most of the vacuum energy, leaving just enough to drive cosmic acceleration that we observe today. In 1998, two teams of scientists set out to measure how much the universe's expansion was slowing down. Instead, they discovered that expansion is speeding up. This discovery won the Nobel Prize and shattered our understanding of cosmic evolution. For decades, astronomers assumed gravity would eventually win its battle against expansion. All that matter in the universe should act like a cosmic brake, gradually slowing expansion until everything either stops growing apart or begins collapsing back together. Teams studying distant supernovae expected to measure this deceleration. Type Ia supernovae explode with nearly identical brightness, making them perfect cosmic lighthouses. By comparing how bright they appear versus how bright they should be, astronomers can calculate precise distances to their host galaxies. When they plotted these distances against redshift measurements, they found something impossible. Distant supernovae were fainter than expected. This meant they were farther, away than the standard expansion model predicted. Somehow, space had grown more than it should have during the light's journey to Earth. The only explanation was that expansion itself was accelerating. Something was pushing space apart with increasing strength. Scientists call this mysterious force dark energy, and it dominates everything. Dark energy constitutes roughly 68% of the total mass energy content of the universe. It outweighs all ordinary matter by more than 13 to 1, yet we have no idea what it is. Here's what makes dark energy so weird. It doesn't clump or dilute. Normal matter becomes less dense as space expands. Spread a fixed amount of matter across twice as much space and you get half the density. But dark energy maintains constant density even as space grows. As the universe expands, new dark energy appears to fill the additional volume. This means dark energy's total influence grows over time. In the early universe, when everything was compressed together, matter and radiation dominated cosmic evolution. Dark energy existed, but its effects were negligible compared to the gravitational pull of all that concentrated matter. As expansion spread matter thinner, dark energy's repulsive influence became more apparent. About 5 billion years ago, dark energy became the dominant force in cosmic evolution. Before that moment, expansion was slowing due to gravitational attraction. After that moment, expansion began accelerating due to dark energy's repulsive push. We live in the age of acceleration. Every day, dark energy becomes more influential. Every day, expansion accelerates a bit more. In the far future, dark energy will dominate so completely that distant galaxies will accelerate away from us faster than light can travel between them. they will disappear from our observable universe forever. The leading candidate for dark energy is vacuum energy, the quantum fluctuations that fill every point in space. Quantum field theory predicts that empty space should contain enormous amounts of energy. Alternative theories suggest dark energy might be a new field pervading space, similar to the electromagnetic field but with different properties. Others propose modifications to gravity itself at cosmic scales. The truth is, we are as ignorant about dark energy as ancient humans were about lightning. Yet this mysterious force shapes everything about our cosmic future. Current observations suggest dark energy has remained roughly constant throughout cosmic history, but the data isn't precise enough to rule out slow changes. Future measurements will determine whether dark energy is strengthening. If dark energy continues strengthening over time, expansion might accelerate so violently that it eventually overcomes every force holding matter together. Gravity would fail first, then electromagnetic forces, then even the strong nuclear force binding protons and neutrons. The universe wouldn't just expand forever. It would tear itself apart from the inside. During the first trillionth of a second after the Big Bang, the universe expanded more rapidly than it has in all the 13.8 billion years since. This period, cosmic inflation, stretched space so violently that regions of the universe lost contact with each other forever. Points that were once close enough for light signals to travel between them were suddenly separated by distances that light could never cross. Nothing can move through space faster than light, but space itself has no such restriction. During inflation, the distance between any 2 points doubled every tiny fraction of time. This doubling happened so rapidly that light couldn't keep up. Inflation increased the size of the universe by a factor of at least 10 to the power of 26. That's like a grain of sand suddenly becoming larger than the observable universe today. This expansion happened in about 10 to the power of negative 35 seconds. To put this timescale in perspective, light travels about 1 foot in a nanosecond. During inflation, the universe expanded by more than 20 orders of magnitude in a time so short that light could cross less than the width of a proton. The energy driving this expansion came from a hypothetical quantum field called the inflaton field. Unlike other quantum fields which have minimum energy states of zero, the inflaton field became stuck in a high-energy state called a false vacuum. This created a temporary form of dark energy far more powerful than anything we observe today. While stuck in this false vacuum, the inflaton field drove exponential expansion. Exponential growth starts slowly but accelerates dramatically. During inflation, every tiny instant space doubled, then doubled again, then again. This process solves several major problems in cosmology. It explains why the cosmic microwave background looks so uniform across the sky. Without inflation's rapid expansion to smooth out irregularities, different regions of the observable universe should show dramatically different temperatures. Instead, we see remarkable uniformity. Inflation also explains why space appears geometrically flat. Even if the universe started with significant curvature, inflation stretched that curvature so much that any remaining bend became undetectable. But inflation's most profound consequence involves quantum mechanics. During inflation, quantum fluctuations in the inflaton field were stretched from subatomic scales to cosmic scales. These microscopic variations in energy density became the seeds that eventually grew into galaxies, stars, and planets. Every structure in the universe traces back to quantum uncertainty, amplified by inflation. The galaxy you live in, the star that warms your planet, and the atoms in your body all exist because of random quantum events that happened during the universe's first moment. You are the descendant of quantum foam, but inflation raises a disturbing possibility. If it happened once, it might happen again. The same quantum fields that drove primordial inflation might still exist, waiting for the right conditions to trigger another episode. This could happen here, now, without warning. A new bubble of inflation could nucleate anywhere in space, expanding outward at the speed of light and destroying everything in its path. Yet this terrifying possibility pales compared to inflation's most mind-bending implication. What if our universe is just one bubble in an infinite sea of expanding realities? While you read these words, trillions of other universes might be inflating into existence, each with different laws of physics, different constants of nature, and different possibilities for life. If inflation happened once, quantum mechanics suggests it should happen continuously, throughout a larger space called the multiverse. Random quantum fluctuations can trigger new episodes of inflation anywhere, anytime. Each episode creates a bubble universe that expands and cools, potentially developing its own galaxies, stars, and planets. Our universe would be just one bubble in an infinite foam of realities. Each bubble universe might have different physical laws. The strength of gravity could be different. The mass of electrons could vary. The number of dimensions of space might not equal 3. Most of these universes would be uninhabitable wastelands. In some bubbles, gravity might be so strong that stars collapse immediately into black holes. In others, gravity might be so weak that matter never clumps together to form structures. But in an infinite multiverse, even the most unlikely possibilities must occur somewhere. We exist in a habitable bubble, not because we're special, but because we can only exist in habitable bubbles. The multiverse contains infinite copies of everyone everywhere experiencing everything. This infinite replication makes the concept of uniqueness meaningless. Yet the multiverse remains unobservable. By definition, other bubble, universes lie beyond our cosmic horizon. Their light can never reach us. We can never prove they exist. The universe might be expanding in directions that don't exist for you. String theory, our most ambitious attempt to unify all physics, requires space to have 9 dimensions instead of the 3 you experience. 6 additional dimensions of space exist right here, right now, curled up so tightly that even particles cannot detect them. These hidden dimensions might be expanding along with the familiar ones. Imagine you're an ant walking on a garden hose. From your perspective, you can move forward or backward, experiencing what seems like one-dimensional space. But the hose actually has 3 dimensions. The circular dimensions around the hose are so small compared to your size that you cannot perceive them. We might be like that ant, aware of only 3 spatial dimensions while 6 others remain curled up beyond our perception. If these extra dimensions exist, they could provide the answer to what the universe expands into. Our familiar 3-dimensional space might be expanding into the higher dimensional space that contains it. Our space might be a 3-dimensional membrane expanding in 9-dimensional hyperspace. This concept, the brain-world model, suggests our entire universe is a membrane floating in a higher dimensional space. Everything we can observe might be confined to this 3-dimensional brain. Gravity alone can escape into the extra dimensions, which explains why gravity is so much weaker than other fundamental forces. The expansion we observe might be our brain stretching within the larger hyperspace. Other brains might exist parallel to ours in the extra dimensions. These parallel universes could be separated from us by less than a millimeter in directions we cannot point to or move in. Another version of you might be reading these words just a tiny distance away in the 4th spatial dimension. Some models suggest the extra dimensions themselves might be expanding, while our familiar 3 dimensions remain static. From our perspective, we would observe expansion and interpret it as our space growing. In reality, the hidden dimensions might be doing all the expanding. The universe might be shaped like a donut, and expansion might be nothing more than the donut getting fatter. General relativity allows 3 possible geometries for space. Space could be flat like an infinite sheet. Space could be curved like a sphere. Or space could be curved like a saddle. Current observations suggest our universe is either flat or so close to flat that any curvature is undetectable. But flat doesn't necessarily mean infinite. You can roll a flat sheet into a cylinder or connect its edges to make a donut shape. If space wraps around itself, then asking what it expands into becomes meaningless. A donut getting larger doesn't expand into anything, it simply becomes a bigger donut. Time itself is stretching along with space, and this changes everything about how the universe ages. When Einstein revealed that space and time form a unified fabric called space-time, he showed us that you cannot stretch one without affecting the other. As cosmic expansion pulls space apart, it also stretches the flow of time. Events in distant galaxies appear to unfold in slow motion compared to events happening nearby. A supernova explosion that takes 3 weeks in a nearby galaxy takes much longer when observed in a distant, rapidly receding galaxy. This happens because the light carrying information about those events gets stretched during its journey. Not just the wavelength of the light, but the time intervals between the light pulses get extended. This creates a bizarre situation where the age of the universe depends on your location. From our perspective, the universe is 13.8 billion years old, but if you could somehow observe from a distant galaxy, our region of space would appear much younger. The early universe didn't just contain more compressed space, it contained more compressed time. Processes that take billions of years today happen much faster in the dense early cosmos. But expansion affects more than just the rate of time's passage. It changes the very concept of simultaneity across cosmic distances. Events that appear simultaneous to you happen at different times, according to observers in distant galaxies. There is no universal now that applies everywhere in the universe. This breakdown means that asking what the universe is doing right now becomes meaningless on cosmic scales. The present moment is local, not universal. The universe is racing toward a state so cold and empty that no process capable of generating energy will remain possible anywhere, ever. This inevitable destination, heat death, represents the ultimate victory of cosmic expansion over every other force in nature. As space continues stretching, it will spread matter and energy so thin that the universe becomes a lifeless void at nearly absolute zero. In about 100 billion years, the last stars will exhaust their nuclear fuel and fade to darkness. No new stars will form because expansion will have stretched matter too thin for gravity to gather new stellar nurseries. After 10 to the power of 34 years, even protons will decay. The atoms that make up your body will spontaneously disintegrate. Matter as we know it will cease to exist. After 10 to the power of 100 years, black holes will become the only significant sources of energy. Black holes evaporate through Hawking radiation, slowly converting their mass into particles and energy. When the last black hole finally evaporates, the universe will achieve perfect heat death. No temperature differences will exist. No chemical reactions will be possible. No life can survive. But there's another possibility, even more terrifying. In about 22 billion years, dark energy might become so powerful that it tears apart every atom, shredding reality down to its fundamental components. This catastrophic end, the Big Rip, would make heat death look gentle. Instead of slowly fading away, the universe would destroy itself in a final spasm of accelerating expansion. About 1 billion years before the Big Rip, dark energy becomes strong enough to overpower gravity on galactic scales. Galaxy clusters dissolve. 200 million years before the end, expansion tears apart individual galaxies. Stars get ripped away and scattered across space. 30 minutes before the Big Rip, expansion overcomes the gravitational binding of solar systems. Earth gets torn away from the Sun. 90 seconds before the end, expansion overcomes molecular bonds. Atmospheres disperse into space. 10 to the power of negative 12 seconds before the Big Rip, atomic nuclei disintegrate. The strong nuclear force finally succumbs. At the moment of the Big Rip, even space and time might disintegrate. The universe doesn't just end, it becomes meaningless. Astronomers measure expansion by turning exploding stars into cosmic yardsticks, using stellar death to map the growth of space. Type Ia supernovae explode with nearly identical brightness, making them perfect standard candles. By comparing how bright they appear versus how bright they should be, astronomers calculate precise distances. When they plotted distance versus redshift for hundreds of supernovae, they discovered acceleration. But measuring cosmic expansion requires multiple techniques called the cosmic distance ladder, with each rung calibrated using the previous one. Different measurement techniques give slightly different values for the Hubble constant, the number describing how fast the universe expands. Local measurements suggest space expands at about 73 kilometers per second per megaparsec. Measurements from the cosmic microwave background suggest about 67. This 6% discrepancy represents a crisis in cosmology. Either one technique contains unknown errors or our understanding is fundamentally flawed. Albert Einstein added a term to his equations that he later called his greatest blunder. That term turned out essential for understanding accelerating expansion. In 1917, Einstein's equations predicted the universe should either expand or contract. They allowed no static cosmos, but everyone believed the universe was static and eternal. Einstein modified his equations, adding the cosmological constant, a term representing the energy of empty space itself, creating outward push to balance gravity. Then Hubble discovered distant galaxies racing away. The universe was expanding, just as Einstein's original equations predicted. Einstein abandoned the cosmological constant, calling it his greatest blunder. But in 1998, astronomers discovered expansion is accelerating. Something pushes space apart with increasing strength, exactly what Einstein's cosmological constant was designed to do. Einstein's blunder became essential for understanding the universe. The accelerating expansion requires dark energy that behaves exactly like Einstein's cosmological constant. Current observations suggest the cosmological constant provides the best fit. If correct, Einstein's intuition about vacuum energy was remarkably prescient. The irony is profound. Einstein added it to prevent expansion, then removed it when expansion was discovered. Modern cosmology restored it to explain accelerating expansion. His greatest blunder became his most prescient insight. Edwin Hubble spent night after night in 1929 measuring distances and velocities of distant galaxies, accidentally discovering that the entire universe is flying apart. Working with the largest telescope in the world, Hubble proved spiral nebulae were separate galaxies millions of light-years away, expanding the known universe from a single galaxy to a cosmos filled with countless galaxies. But as he plotted galaxy distances against velocities, Hubble noticed every galaxy was moving away. Every single one showed redshifted light indicating motion away from the Milky Way. More disturbing, the farther away a galaxy was, the faster it receded. Galaxies twice as distant moved away twice as quickly. At first, Hubble interpreted this as motion through space. But this created impossible problems. If all galaxies moved away from us, we'd occupy the special center of the universe. The resolution came from understanding that space itself was expanding. Galaxies aren't moving through space. Space stretches, carrying galaxies along. Hubble's discovery transformed our understanding. We don't live in a static, eternal universe. We inhabit a dynamic, evolving cosmos that began in a hot, dense state and has been expanding and cooling ever since. Hubble's law became the foundation for Big Bang cosmology. There exists a precise amount of matter determining whether the universe expands forever or collapses. This critical density equals about 5 hydrogen atoms per cubic meter, almost perfectly empty, yet this tiny amount determines the ultimate fate of everything. The physics comes from competition between expansion and gravity. Expansion carries galaxies apart. Gravity pulls matter together. If the universe contains more than critical density, gravity wins. Expansion slows, stops, and reverses into a big crunch. If less than critical density, expansion wins. The cosmos expands forever, approaching heat death. If exactly critical density, expansion asymptotically approaches zero velocity but never stops. For decades, measuring actual density became cosmology's holy grail. Count all matter and divide by volume occupied, but most matter appears invisible. Observations revealed galaxies contain much more mass than visible stars suggest. This invisible mass became known as dark matter. When cosmologists included dark matter, they found a universe with about 30% of critical density, suggesting eternal expansion. Then came dark energy discovery, fundamentally changing expansion dynamics. Current observations suggest we live in a universe with about 27% dark matter, 68% dark energy, and 5% ordinary matter. We're balanced almost exactly on the edge between different possible geometries. This near-critical density creates the flatness problem. Cosmic inflation provides a possible solution. During inflation's exponential expansion, any initial curvature gets stretched so flat that the universe emerges very close to critical density. The question, what is the universe expanding into, is like asking what's north of the North Pole. Understanding why reveals the deepest truth about reality itself. When you ask what the universe expands into, you're assuming expansion requires pre-existing space to expand into, like a balloon needing air or a city needing countryside. But the universe is not like a balloon. The universe is space itself. When space expands, it doesn't grow into something else. It creates the very concept of something else as it grows. There is no external arena because the universe defines what external means. This isn't a limitation of language or imagination. It's a fundamental feature of reality. Before expansion, the concepts of into and outside don't exist. Expansion doesn't just create more space. It creates the logical framework that makes spatial relationships meaningful. The universe doesn't expand into anything because it